Okay, let's do some more curve sketching, and this time, inside of this problem, we're going to need to realize something called L'Hopital's rule. And we should just mention for a moment that when you're taking a limit to a c or infinity, some number or infinity of some function, and you get infinity over infinity or 0 over 0, then this is called indeterminate, and you can't determine what the limit is. Indeterminate. And you don't know what the limit of this function is until, actually I didn't quite state this just right. Yeah, it's a function, but it's actually a quotient of functions. It's like something that looks like f of x over g of x. And you get infinity, infinity, or 0, 0. Then what you do is you say that this limit is going to equal the same limit. It's going to the same limit value, but evaluated at the derivatives. And this, so what happens is you're going to take a limit to try to learn about, some action of the graph, and you get this indeterminate form, and so you can't determine what the limit is until you take the derivative over the derivative. And we have to be careful because this is only true if you get indeterminate form. So we're going to see this inside the middle of this problem. It's actually section 4.4 of the Storz book, but I'm doing some curve sketching from section 4.5. I'm just jumping right into it, and I'll just show you L'Hopital's rule when it comes up in the middle of the problem. So in this problem then, we need to get a sketch of y equals to ln of x over x squared. First thing we need to realize now as we get into the solution, it's all that stuff about the intervals of increase and decrease. Remember all that stuff? The intervals of increase and decrease. The intervals of concavity. Local max and mins. Inflection points. All that stuff. Okay. So anyways, we start these the same way. Of course, sometimes it's good to, as we get into the solution here, to just start right off thinking about the domain. And here, x can't be 0. Well, of course, x can't be 0 in the ln function anyways. X needs to be positive. So we've got, x needs to be greater than 0. So this is to say we're going from 0 to infinity. Right? Because you can only log positive numbers. And the positive numbers will take care of that denominator as well. So then now we start this. Okay, another thing we might want to realize is, that factor of the x squared equals 0 in the denominator. That's going to make a vertical asymptote. At x equals 0. Now we need to wonder, is there a horizontal asymptote? So to make that determination, you take the limit as x goes to infinity and negative infinity, but we'll start with positive infinity. Now see how when x goes to infinity, this is the ln of infinity over infinity squared. This is infinity over infinity. This is called indeterminate form. So we apply L'Hopital's rule. That's section 4.4. And so this is going to equal, still the limit as x goes to infinity, but now I'm going to take the derivative, right? So what I'll do here is I'll put the equal sign and I'll put a capital H over it. And that's usually, how authors show that you've applied L'Hopital's rule. And you're taking the derivative of the top over the derivative of the bottom. it's not the quotient rule, because now you're just literally just taking the, so they're going to equal the limit as x goes to infinity. The derivative of the ln is the 1 over, and the derivative of x squared is 2x, right? It's not the quotient rule. So then we got, this is the limit as x goes to infinity of 1 over 2x squared. Now this is definitely, 1 over infinity, which is 0. So that's how we realize now there's a horizontal asymptote at y equals 0. See, to find horizontal asymptotes, you take a limit, right? You take the limit as x goes to positive and negative infinity. We still have to look at negative infinity, but it's usually the same. That's how we look for horizontal asymptotes. But then when you're taking that limit, if you get this indeterminate form, which is 0 over 0 or infinity over infinity, you apply L'Hopital's rule, which is you take the derivative of the top over the derivative of the bottom, look at that same limit, and then it'll usually work. And if it still doesn't work, you can take the derivative again. You can just keep applying L'Hopital's rule again and again until this thing resolves itself. So now then it's time to take the first derivative. So my function then, if you remember, my function here is ln of x over x squared. So f prime is low d high minus high d low square the bottom. So this is x squared over x minus 2x ln of x over x to the fourth. This is x times 1 minus 2 ln of x over x to the fourth. So this is 1 minus 2 ln of x over x cubed. Now there's your first derivative. Don't forget that what we're doing is we're looking for our critical numbers now. When we take the first derivative and say, where does it equal 0? Well, that's going to happen when 1 minus 2 ln of x equals 0. That's going to happen when 2 ln of x equals 1. That's going to happen when the ln of x equals half. Well, this is x equals e to the 1/2. Remember? Because logarithm is an exponent, so whatever the log equals is the exponent. So I know 1/2 is the exponent. The base is e, so I know I got e to the 1/2. Well, that's what x equals. So this is one of our critical numbers, and it's a weird one. Also, don't forget that for critical numbers, we want to know where is the first derivative undefined. And that's going to happen when the bottom is 0. That's going to happen at x equals 0. So we got two critical numbers here. But, okay, actually, I got to be careful about that. Because remember how x equals 0 is not even in the domain of this function? Remember how our domain is only talking about x is greater than 0? So, x equals 0 is not in the domain, so it can't be formally, it can't be a critical number, right? So note, x equals 0 not in domain. So x equals 0 is not a critical number. Even though I'm still going to keep an eye on what the function does right there. Matter of fact, we already know we got to keep an eye on what it does right there because we're expecting a vertical asymptote. That x squared in the denominator is going to make a vertical asymptote on us. So here then are, getting at our critical numbers. So now it's time to play the first derivative test. So I'm going to take e to the 1/2. By the way, I'd like to just roughly know what that number is. This is, it's about 1.6. It's nice to know that because this e to the 1/2 being about 1.6 means that when I want to choose a number to the left, so remember we have to be in the domain, and the domain is only numbers greater than 0. So I need to choose a number in this interval, it's greater than 0 and less than 1.6. 1 is a nice one. See, it was nice to know that e to the 1/2 is about 1.6, because that way I could choose a nice test number here. Now a number greater than 1.6, like 2. And we're going right into the first derivative with this. So we're putting 1 into there. Well, the ln of 1 is 0, and 2 times 0 is 0, so this is 1 minus 0. This is a positive on the top. And putting 1 into the bottom, we're testing 1, remember. 1 cubed is 1, which is positive on the bottom. So that positive came from the 1 minus 2 ln of x. And this positive came from the x to the 4th. Positive over positive is positive, so this tells us the first derivative is positive in this interval, so the function is increasing. At e to the 1/2, that was where the first derivative was 0, so I know there's a horizontal tangent right there. And now I'm going to test in 2. Well, the ln of 2 is some number bigger than 1, and when I take 2 times a number bigger than 1, hold on a minute, the ln of 1 is, excuse me, it's a number, actually I do have, you kind of have to check this. You have to check this at 2. I need a calculator for this. I'm testing my test value 2 into the first derivative. So I need the ln of 2. So I'm going 2, which is about 0.69. Now I'm multiplying that by negative 2. And going and adding that to 1. And this is negative. So that one you really had to, that's the first one I really had to test so carefully to realize that's negative there. A nicer would have choose, you know what a nicer test number would have been to choose? If I had tested e, because then this would have been the ln of e, which is just 1, and I would have gone 1 minus 2 is negative. I would have made the realization just in my head. But anyways, here we are with 2 cubed is positive. So we got a negative over a positive, which is negative, so the function is decreasing here. Now don't forget, at x equals 0, there's a vertical asymptote, so we're thinking it's going like down the asymptote like this. Could be something else going on there when we see the second derivative, but this is all we got for this thing so far. Now we got to take the second derivative and find the intervals of concavity. I'll need another page for that. So then we're continuing with this problem now where we had our f of x. This is a curve sketching problem where we had our f of x was the ln of x over x squared. We found f prime of x, 1 minus 2 ln of x over x cubed, and now it's time to find the second derivative. So we got low d high, well the derivative ln x is 1 over x, so this is minus 2 over x. Low d high minus high d low square the bottom. And so here we got a negative 2x squared. Here we got a minus 3x squared. And a plus. Negative times a negative plus, and we got a plus 6x squared ln x. All over x to the 6th. So we got a negative 2 minus 3 is minus 5x squared plus 6x squared ln of x. So here then we can pull out the negative x squared, and we got 5 minus 6 ln of x. So these two are going to factor with 2 of those, cancel with 2 of those, so we got 4 factors down there, and this is a negative 5 minus 6 ln of x. So now we got the second derivative, and it's time to start setting it to 0 and find those intervals of concavity. You know, don't forget as you're doing this, you know, first of all, I didn't mean to make the number line because we're not quite done with this, because we got to find where is this equaling 0. Where does this equal 0? That's when 5 minus 6 ln of x equals 0. That's when 6 ln of x equals 5. That's when the ln of x equals 5/6. Whatever the log equals is the exponent. The base is e, so this says e to the 5/6 equals x. That's one of our critical values, one of our critical numbers. The other one comes from where is the first derivative undefined. And that happens when x to the fourth equals 0, which is when x equals 0. So, but don't forget x equals 0 isn't even the domain of the function, so, you know, its formally can't be any critical number. So really our only critical number is e to the 5/6, which, by the way, is approximately, it's approximately 2.3. So even though x equals 0 is not a critical number, I'm still going to put it on the number line right here, because something funny is happening there. If you remember, there's actually a vertical asymptote there, and then we don't go to the left of there because the domain was only all x is greater than 0. And now we got this e to the 5/6, which is about 2.3. So now we need intervals, you know, we need to try numbers, test values in these intervals. So, you know, in between 2.3 and 0, I would test 1. And something greater than 2.3, you know what's a nice one? Is 2.7, in other words, e. Because it's going to make this ln part easy, like I didn't think of to do on the last page there. So, this is what I'm testing. So we test 1 into this first derivative. Don't forget there's this negative outside, so this is this negative right there, the negative outside. Now we got the ln of 1 is 0, so 6 times 0 is just 0, and this is 5 minus 0, which is 5, which is positive. So you got the negative times a positive up there. And on the bottom, 1 to the fourth is positive. Negative times positive is negative, and negative over positive is negative. So we're concave down here. That means, you know, the function is concave down to the left of 2.3. And now we're testing an e into the first derivative. So we got the ln of e, which is 1. 5 minus 6 is negative. But don't forget there's this negative out here. And we're over, you know, e to the fourth, which is going to be positive. So negative times a negative is positive. Positive over positive is positive. So we're concave up on this interval. And there is an inflection point right here. Right where the graph changes from concave down to concave up, and this is a value in the domain. So we got e to the 5/6, and then we're going to have to find f of e to the 5/6. Might as well just do that quickly right here. So we got e to the 5/6, and now this is going to be the ln of e to the 5/6 over e to the 5/6 squared. Freaking weird number. Well, this ln of e to the 5/6, this is 5/6 times the ln of e, this is 5/6. And this is e to the 10/6, otherwise known as 5/3. So this is like, you know, 5 over 6 e to the 5/3, a real weird freaking number, but there it is. This is e to the 5/6, comma, 5 over 6 e to the 5/3. That's where that inflection point is. And you got to be able to find that in exact form like this, not just some calculator approximation. So we're just about winding this problem down then, because we got that it's, you know, it's increasing. Might as well just get the sketch and then read this right off the sketch. There's a y-axis and an x-axis. Oh, by the way, see the local max right here? E to the 1/2. Here's another one. We need to know f of e to the 1/2 to, you know, to get where that local max is right there. So f is the ln of x over x squared. So at e to the 1/2, this is the ln of this is the ln of e to the 1/2 over e to the 1/2 squared. So this is 1/2 the ln of e. This is 1/2 over e to the 2/2 over e. This is 1 over 2e. So this y value here is 1 over 2e. So see those little details there that you would overlook so easily, like this little scratch work that I just did here to get the y value. The same thing over here, what I did to get the y value on that inflection value right there. Little places like that, you know, you shouldn't be stumbling at your level on that stuff anymore. So anyways, we have a local max. By the way, 1 over 2e So 1 divided by 2 divided by second. Whoops. We gotta take, there's E. We'll take E to the -1. There's 1 over E. And now multiply that times a half. So anyways, it's about 0.18. So this problem's a little weird, whatever. So this local max is at about 1.6.18. So this is E to the 1/2, 1 over 2 over E, right? It's about 1.6, 0.18. Anyways, that's where there's a local max. And this thing is concave down. See how it's concave down to the left of e to the 5/6, and e to the 5/6 is about 2.3. So this is 1.6. Somewhere over here is about 2.3. And see this value here, 5 over 6 e to, we don't have to fuss over that too much. It's a value that's positive, and it's less than 1. So I mean, you can bet it's going to be it's going to be about here. And that's where the inflection point is. So look, to the left of there, it's concave down. So that's why it's going to be going through that max and then down the asymptote here. And to the right of it, it's concave up. But don't forget, there's a horizontal asymptote here. See, there's a horizontal asymptote, and we found that there's introducing L'Hopital's rule, which is important. We found that the horizontal asymptote y equals 0. So it's going to be concave up to the right of e to the 5/6, but it's going to approach that horizontal asymptote, so it's coming down like this. See how it's actually concave up right here? I would exaggerate it a little bit, but it'd be hard to see the asymptote anymore. See? It's concave up right there. That's to the right of e to the 5/6, and it's concave down to the left of e to the 5/6. See? Concave down. And it's got this max at about 1.6.18. So that's a lot of fuss just to get this sketch, but all that stuff has to be just right.